Hello, everyone. Welcome to TMLS MLOps 2021. Hi, Gennady. Our speaker today is Gennady Pekhimenko. He's an assistant professor at the University of Toronto, the CS Computer Science and ECE department, where he's leading the Ecosystem Efficient Computing Systems group. Gennady's also a faculty member. I'm hearing an echo. Is that is just okay? I'm sorry. I'll keep going. Gennady's also a faculty member at the Vector Institute and a CFAR AI chair. Before joining the University of Toronto, he spent a year in 2017 at Microsoft Research in Redmond in the Systems Research Group. He got a PhD from the Computer Science Department at Carnegie Mellon University in 2016. Gennady is the recipient of the Amazon Machine Learning Research Award, Facebook Faculty Research Award, Connaught New Researcher Award. He's an NVIDIA graduate, Microsoft Research, Qualcomm Innovation, and INSERC CGSD fellowships. He holds those. His research interests are in the areas of systems, computer architecture, and applied machine learning. I leave it to you, Gennady. I'm looking forward to your talk.
Thanks a lot for the introduction. I hope everyone can hear and see my slides. So it's a pleasure for me to talk today. I'm going to talk about some of the interesting research me and my students are doing in our ecosystem research group. So the title of today's talk is Machine Learning Tools, Skyline and Aeroscope. So those are two artifacts that we build, among other things, in our group, and then I'm going to talk about them in detail and give some pointers to other type of research we do in the group moving forward. So let's start. So a lot of things we do in my group is that we're trying to run ML application faster. And to do that, you need to perform analysis and optimizations of them. So in order to have that, there are several pieces that needs to work in sync so that you can do that. So you need to have a diverse set of benchmarks, right? Those are needed to measure the key performance metrics. And to measure the metrics, you need to have the tools. This is the part I'm going to mostly talk today. And in order to build the tools, you need to know what are the right bottlenecks so that the tools would reflect those. And the bottlenecks require the benchmarks. So that was the original dependence back in 2016 when I started to work a lot on machine learning. That was a big problem. That loop was not really resolved in any way. So there was too many dependencies clearly. And the first thing my group and some collaborators at Google and Stanford work on was building a diverse benchmark suite. I'm not going to talk too much about it. I've just said that we spend a lot of time working on that, do some publications on the topic in collaboration with Microsoft Research. So we have our benchmark suite built and open source and available online called TBD suite. So it's called TBD because it's training benchmarks for DNN and also for to be done because every time you release the benchmark suite, it's already kind of late. You already need to upgrade it. So those are the models we have there. You can experiment and test them if you're building a software or hardware stack for your applications. You can use and test them. We also are active participants in the MLPerf ML Commons initiative, which is a de facto standard for machine learning benchmarking. And we essentially work there on benchmarks, dataset, and best practices. We publish papers there. So there were one papers on machine learning training benchmarks recently at MLSys conference last year. We also work on the inference benchmarks as well. And there's things there. If you're interested about that, please reach out to me. I'm still heavily involved in MLPerf. I'm one of the co-chairs and on the board of the ML Commons. So when you have benchmarks, then you can measure the key performance metrics. So what are those metrics that you care about? Obviously, from the ML perspective, you care about accuracy of the model. But beyond that, from the systems perspective, what are those important metrics are? You care obviously about throughput, so how quickly you process the data samples when you perform training, so how many samples you process per second. You care about obviously compute utilization, some of the fancy compute unit utilization, such as Tensor Core on GPUs. And obviously, if you want to run really large model, you care about where the memory goes, because frequently you can get out of memory. So those are the typical performance metrics people care about. But for them to be measured efficiently, you need to have the right tools. And this is the primary focus of today's talk. So the first I think I'm going to talk today is Skyline, which is an interactive in-editor performance visualization and debugging tools for DNN training. It was done by my student Jeffrey Yu. And the focus of Skyline is to work on the regular, supervised learning algorithm. And it was a paper on that at U East last year. So what's the motivation? So a lot of people are tired of not knowing why their model is either very slow from runtime perspective, or why it uses so much memory that you can frequently get out of memory. And you are not alone if you have that problem. There are a lot of people that complain online about not understanding why their PyTorch models are so slow, why it gets out of memory, and they were lacking tools to solve the problem. So the goal of Skyline is to provide you those key performance metrics in a nice and visual way to be able to nicely navigate the code of your model and to be interactive and proactive and live as you develop the model. So it's built on top of PyTorch Atom Editor, but it can potentially build on top of any framework or an editor, because it's not having heavy dependence on it. So how does it work? Let's go one by one. So how are those key high-level performance metrics reported? So essentially, this is your code. This is a demonstration on the very well-known ResNet models. On the right-hand side, we are showing essentially a tab that shows the maximum, the throughput you can achieve right now with the model you have. And this is the predicted maximum you can on that GPU that you have, that you are doing the experimentation. And this tells you about how well you utilize your memory. So in this case, we only use about 1.5 gigabyte out of available 8 GBs on the GPUs that we had in this experiment. So they are nicely and easily shown here. Then there is an iteration, runtime, and memory breakdown. So for each line of your model, right, as you execute it, you can click on those dots here and can get detailed information on where the time goes and where the memory goes. As you can see here, we have a breakdown on the forward and backward pass. We had the breakdown of the memory, say waits versus activations versus other parameters. And all of that is nice and convenient for you. So it's very easy to develop using Skyline. It's also interactive. As you can see, you can click on all the layers, you can click on different components, and they will show you their total runtime contribution of the total runtime. And moreover, it even links to the batch size. So for example, if you drag the throughput, if you go and get higher throughput, we actually can change the batch size for you. So let's zoom in and look a little bit more carefully how that works. So it's live in the sense that all the profiling happens on the fly as you edit the model. So as you make the changes, right, you immediately can see the net effect of that, right? So you don't need to run and wait for hours for the profiling to happen. It all happens on the order of hundreds of milliseconds, right? And it's even connected with the code. So if you want to better get higher throughput, you can just drag like one of those things here, and the batch size will automatically change. So Skyline is open source. This is just another demonstration of how the batch feature works, right? You don't even need to search for it. It will automatically update some of your key hyperparameters that affect the system level performance, not the ML side of performance. Okay, so this is how the Skyline works. It's quite efficient already. We also integrated with the tool called Habitat, and the Habitat is an extra plugin to Skyline that can make prediction how better you run on a different GPU or even TPU. So for example, if your GPU is 2070 and this is the throughput you get right now, specifically for your model, we can make a very accurate prediction on how well you're going to run on something like V100 versus P4 or any other GPU that you might use. And this paper just got recently accepted to Unix ATC conference, so we'll open source the code as well. Okay, so Skyline is a very powerful tool for supervised learning that a lot of people are using right now. but there is an emerging class of new models coming from a different domain of reinforcement learning or unsupervised learning in general. And for that, the existing tools, both that one we build or the one that NVIDIA provides, are not sufficient. I'll show you why in the next 10 minutes. And with that goal, in collaboration with our colleague at Harvard, we built a tool called ArrowScope, also open source on the link provided, that is a cross-stack profiling tool for reinforcement learning. So I just told you about Skyline and said how good it is. Why can't we use it? So we'll start with a few, a quick animation on why reinforcement learning matters. So the past decade has a lot of promising advancements in reinforcement learning. So the Atari game, the expert level of playing the game of Go. So being able to beat, AlphaGo was able to beat the world champion in Go. And there are robotic locomotion, and there is data center management, where reinforcement learning is recently used. Very recently, I think Google starts to use reinforcement learning even to build their new machine learning hardware, like TPUs for design. So reinforcement is definitely useful. And it's progressing, but what are the problems with it if you actually want to deploy and use it? And if you ever try to use reinforcement learning in your own research or development, you will face those challenges. First of all, training time is ridiculously slow, right? It might take 40 days to train AlphaGo 0 on 4 TPUs. And you need to try many different algorithms before you train the model. So that's very time consuming. Another problem is a lot of people think that reinforcement learning is the same as supervised learning. So just make your GPU run fast, right? Or your TPU run fast. But there is a fundamental difference between supervised learning and reinforcement learning. In the supervised learning, you're provided with a bunch of labeled data, right? That works quite well. On the reinforcement learning, though, all the labels, essentially you need to call the training data, you need to collect on the fly using the simulator, right? So another problem is that the profiling tools designed for supervised learning always assume that you're going to be accelerator bound or GPU bound. And that makes those tools like NVIDIA Insight tool, for example, or NVProf, the old name for that tool, not extremely efficient or even misleading when working with reinforcement learning. So existing tools limited to bottleneck layers, and in reinforcement learning, CPU times matter a lot. So profiling overhead needs to be handled because you frequently context switch between Python level code, for example, and C++ code. And the profiling overhead can be so high that it leads to almost 2x, runtime inflation that makes all the predictions you make or analysis you make irrelevant. So when people ask why just not the existing tool for supervised learning, the short answer is these workloads have fundamentally very different structure. So what is the structure? So what's the difference? So let me show the head-to-head comparison between supervised learning and reinforcement learning. And for examples, I use image recognition for supervised learning. And for reinforcement learning, I use Atari Pong game trained with DQN algorithm. And the separation here would be between Python front end and C++ back end. So the way supervised learning works, the model is initialized on the Python level with the computational graph, for example, using Keras or any other framework you like. And then you invoke mini batches of data being processed directly in C++ level. And that's where the backpropagation happens. And that's where your GPU is efficiently utilized. What's the difference between reinforcement learning? Well, the reinforcement learning, you have your simulator that runs in the C++ layer typically, and that provides information back to the Python level that triggers inference in the C++ level that computes some important parameters in the inference that now needs to be reverted back to the layer of simulation that is located in the Python side. And that has to go back to the Pong simulator in C++ and going back again for the cached experience that does something on the Python level and you have to go back again to C++ level to do the backpropagation. So as you can see, there is a lot of cross-stack jumping between Python frontend and C++ that makes it extremely inefficient. And everything is much more efficient on the supervised learning. So if you have to summarize the differences, key fundamental difference between supervised learning and reinforcement learning, what you're going to see is the first difference is the way the training data is collected. In supervised learning, all of your training data is already given to you, labeled to you, and you can just feed it through your accelerator. Here it's very different. You need to collect some information in your simulator, which is a standalone, binary running some, executions, and then you need to feed it back and cache the experience on the Python level that process it to make next decisions on where to move further. Then another problem is the training loop. The training loop for reinforcement learning is much more complicated than that of the supervised learning. And another thing that is an important difference is the size of the model. So the models using image recognition is usually very big models like ResNet 50, like a lot of large convolutional layers. And in contrast, here there are going to be a lot of backpropagation inference, but models are very thin, so it means the GPU is not utilized that well. So those are the key problems. And obviously the question is, the first time you take the RL workloads, where does it spend its time when you run it? And that's, to answer this question, essentially it's very tricky. You need to build a new cross-stack profiler that can capture all that complexity. So essentially, software stack here consists of the algorithm, backend, simulator, CUDA API, and CUDA kernels. And there is a hardware here, CPU and GPU or TPU, that used to run this. And in RL scope, we actually aim to handle that well. So how the RL algorithm looks like. Don't look at the code itself. What you need to understand, there are three major pieces in every RL algorithm. There is an inference where you see how well you perform. There is a simulation where you do measurements, right, on the model. And there is a backpropagation that updates the model based on the results from inference and simulation. And all of that splits across different layers. So this is why cross-stack scoping is so important, so you can understand where resources are going, and that's why it's so difficult to do. So what RL scope provides you? RL scope provides you features that can go across all these layers, so you can understand where the CPU and GPU time is spent across each layer. It works across different frameworks, so it supports TensorFlow, PyTorch, and multiple different simulators. It's also capable of correcting for profiling overhead that I mentioned, that the CPU overhead can be really huge and can make wrong insights. And the main contributions we made here is really, we build an open source tool that we shared with the community. You can use it now and profile your RL workloads if you're using it. And we did an extensive survey with the people who are using reinforcement learning to show how we can speed up their stuff. So let me show you how you would actually use it. So RL scope needs really minimal information from the developer. So the only thing we need is this simple annotation where you would tell us literally which of the part of the code is simulation, which is inference versus backprop. You can't really figure out it automatically. That's difficult. So just add these three annotations, and that's pretty much what we need from the user. So that would allow us to generate understandable output for you, where we would say this was a runtime was in simulation versus that was an inference. So also all the interception is transparent. So we intercept all the calls from the CUDA libraries, CapTI, and making sure we attribute them to the right thing, whether it's CPU, GPU, Python, or CUDA, or the backend. And that's all transparent. You don't need to recompile anything or change anything, right? It makes it very easy to support multiple frameworks and simulators. Then we perform overhead calibration and correction. It's a very important thing because when profiling is disabled, your runtime might look like this on the left-hand side here. But as you start to add runtime, measurements of data collection, you get all this overhead, and it's maybe very non-uniform. So you get some extra overhead, and you need to do it for a lot of different events that you need to collect. So you need to compensate for this overhead somehow. So this is something we do. We detect where this overhead is, and we're able to compensate for that overhead of the runtime. And it's very non-trivial because of the how much overhead low-level tools from NVIDIA add to the runtime. Another important thing is we do cross-stack event overlap. So we don't just tell your CPU time is 10%, your GPU is time 90%, or vice versa. We actually show you the total training runtime and how it's spanned across all these different layers. We span that, for example, here you in Python, running on the CPU, and here you are right now in the inference stage, and you are still on the Python. And then you move on, and then here you're in between CPU and GPU, probably communicating data, and then you're running the GPU kernel. So you're actually doing something useful on the back end, and so on. So overall, as you can see, that can give you very accurate insight on where everything happens. And in our paper, we will demonstrate a lot of different use cases, how things work. So you can look at resource overlap, you can look at how well your CPU, GPU runtime is consumed, and whether that's what you expect when you design the algorithm. And we performed an extensive workload study, and the application we look for was essentially PyTorch and TensorFlow, and we look at the Atari Go game and robotics applications as well. So let me show you one case study in the interest of time. I'm going to go into all of them. So just a reminder for everyone. So PyTorch and TensorFlow both support eager execution. So what does that mean? It really means that as you go, you execute each of them line by line, right? And then you generate the results. In contrast to that, TensorFlow has a well-known graph model that's much more efficient. You build the graph first and then you execute, but it's a nightmare for debugging if you want to change something. So PyTorch is very well known that it's easy to debug. So TensorFlow proposed out a graph model recently that uses a hybrid approach. So let's say you want to compare which of these approaches work well for reinforcement learning. How would we do it? That's what RL Scope can help you. So RL Scope can provide a very accurate information on what's running where. For example, we can quickly find that neither outer graph nor graph outperforms the other one. They're within 20% of each other. We can also find that eager execution is significantly slower than the outer graph and graph execution, not surprising. But we not only find how much it is slower than a lot of other tools can tell you, we also can find the reason why it happens. And the reasons are because of how many transitions between Python and front end and the back end happens. So we not only can give you how much faster your code is, we can also attribute what exactly in your code make it fast or slow. Okay, so that's essentially what the RL Scope can give you. It can also compare, for example, PyTorch versus TensorFlow, and it can say that PyTorch eager execution is 2x faster than the TensorFlow eager. Why is that? We don't need to speculate, as a lot of other work previously did. We can attribute it to the many transitions that happen between the Python level and the backend level. And PyTorch essentially can handle those transitions much more efficiently. This is why you can see on the graph that PyTorch would be more efficient than the TensorFlow when compared back to back. Okay, so this tool essentially gives you quantitative metrics in your hands so you can fairly make their comparisons. Overall, you can see that at most 14% is spent executing GPU kernels, and that's quite low. Okay. And that's also explained why reinforcement learning are not that efficient running on GPUs, because they're using only 14% of the runtime at most on the GPU. The rest is sitting on the CPU, right? And CUDA API runtime dominates kernel execution. That's another observation we made here. So RL Scope will allow you to explain the performance differences for your models and explain and correlate that with transitions, and it will help you to fix that if you want. And there are more details about that in the paper. So in summary, The key takeaways here, there is very little time running on the GPU kernels when using reinforcement learning, and that's because of the frequent transitions. Backpropagation spent, again, only 14% of time, and at least 38% of training time is spent in simulation. So running your simulator efficiently is very critical for those workloads. That's very different from supervised learning, where all these labels are given to you. Okay, in the interest of time, I'm going to skip over other experiments and just make a quick summary. So essentially, I present two tools today: Skyline, interactive and editor performance debugging tool, and Arrowscope, cross-stack profiling for reinforcement learning. Both tools are open source, and if you're an active ML developer researcher, we encourage you to use the tools to improve the performance of your model. And just to finish it up, all this work was done with amazing students of mine, both PhD, masters, and bachelors. They're actively working on all these tools, and we are planning to commercialize them eventually. That's it from me. Thank you. Happy to take questions now.
Thank you so much, Gennady. That's amazing. That's really interesting. It's beautiful too. Like, I could see how you'd get kind of addicted playing and then trying to keep improving your performance. It's just gorgeous. I'm also not surprised to hear you plan to commercialize it in the future. I was wondering that. It's certainly got a lot of potential. So Adrian asks, would Skyline run in VS Code?
VS as in, can you elaborate, Adrian? Is it like Visual Studio? What do you mean by VS?
So hopefully Adrian is listening and he'll type into the chat. Yes, he is. Visual Studio Code, he says.
Yeah, it can be. It's not implemented right now. Again, that we don't have the resources yet to integrate it with a lot of different editors. And Visual Studio is actually not the most popular editor used for development, but it can be. We really had very limited dependence on the specific editor. We just need to know which line has which line of code, and the rest is independent from that. We're already connected to several different editors. So another question from Marco, I can see, can you use Skyline to optimize inference performance as well? Marco, yes, you can use it for inference. There is nothing like we can use just inference or inference and backward pass. Just for inference, profiling is usually much easier, right? Because inference, if you take one input, the inference would be running on the hundreds of milliseconds, and it doesn't have that complications of the backward pass. But it can be used, so we can give you the same information for inference, right? It doesn't also have this complication with the memory footprint.
So Rajiv asks, like Habitat, is there an integration of Skyline with Apache TVM? If that question makes sense, he adds.
Yeah, we actually working on TVM with some other projects. I didn't have time to talk about what other research we do, so we are actually active contributors to TVM. So TVM has a solid stack right now supporting inference, but not training, right? So eventually, when TVM is more mature and would have support for training, it would make sense to merge, Habitat with TVM, right? There is also tools from Amazon that develop, like such as SageMaker, where things like Habitat is very useful. For example, like there are more and more hardware arriving right now, right? You all know about TPUs. There is a hardware arriving from Amazon called Trainium. There is DaVinci chip from Huawei. There is a chip from Habana that's part of Intel right now. And at some point, you need to make a decision which hardware you want to use. So things like Habitat can allow to make a prediction on whether that's useful for you or not without trying the hardware, right? Without access to it, which is very helpful, right? But before doing any development and purchases, you can see how helpful it is for your specific model.
So keeping up with all of these hardware developments is probably part of the outstanding research direction that you focus on. What are the big open research questions? Like what do you spend your time really thinking about and working on in your mind?
Yeah, so I had good slides about that, I guess. So there are several different things. I don't see any other questions, so I can just give me a second. So there
While
are,
you're doing that, I'll just remind everybody who's still with us, thank you for coming. And the organizers would really appreciate it if you could fill in the poll. You'll see it, you'll see chat polls and people off to the right. And if you could let the organizers know if the session was useful, that helps them for planning in future sessions. Thanks for that. Okay, great.
yeah, there are several important problems. I'll just show one slide for each work. So first of all, it's very tricky and difficult to scale by propagation. It's not an easy problem. So we work on that, how to scale large models on existing hardware. So that's DPSA paper. It's also open sourced code. Then we work on distributed training. Another big problem is memory footprint. So we had 2 papers and 2 projects that specifically dedicated to reducing memory footprint. So when you train, the memory of your GPU can be very limited. So we had 2 recent papers on how to reduce memory footprint. And it's not just papers. The code was released and is part of the main branches of frameworks like MXNet and PyTorch. And we also work on new optimizations when you, for example, train multiple different versions of the same model. We do hyperparameter exploration. So we build a very efficient way to train those models, not one by one, but collectively. Those are the interesting. And we also work on training at the edge. So this is the most recent work where we show you can actually train models even on your smartphone, like your Samsung S10, for example. Yeah. There are a lot of interesting work, and I'm happy to talk with the people interested. We're always open to talk.
Excellent. Yeah. Thank you.
If you're interested, reach out to us.
Maybe just put your slide up for contact information, just to make it easy for people to reach out. That was fantastic. Beautiful. So interesting.
My first name and last name, good hashes. So if you just entered me, you're not going to get any collisions. Okay.
Thanks so much, Gennady.
Thank you, guys. Bye.